Okay, so last week we started talking about this energy equation. Our ultimate purpose, by the way, why we are doing this will be clear maybe today or tomorrow, by the end of tomorrow's class, is that we are trying to obtain a set of equations uh, to which we can use to calculate or to relate the conditions before conditions after a normal shock wave to the conditions before the normal shock wave. So that's where we're going and why we're doing these discussions here. Now, of course, energy equation is important, and um, we have actually seen the energy equation, which was basically along a streamline. And let me remind you our conditions for a steady, adiabatic, and inviscid flow along a streamline from point 1 to 2, as you can see from here, regardless of the fact that, so let me mention this again, I mentioned this last time as well. So regardless of this, of the fact that there could be a shock wave or there is no shock wave, the stagnation enthalpy from 1 to 2 will be constant because of the fact that when even if there is a shock wave, the flow is still adiabatic. There is no external heat addition to the flow, and it's steady state inviscid flow. So because of the fact that it's adiabatic, H0 stagnation enthalpy does not change is our starting point. So we started from here, stagnation enthalpy definition, so static enthalpy plus the kinetic energy basically, and then opened up the static enthalpy, replaced CP definitions with gamma and R equations. And then since we have also discussed the definition of speed of sound also last week, now we see in these equations speed of sound as well. And of course, as you might guess, that we can turn this into a Mach number as well. So for two distinct points along a streamline from 1 to 2, regardless of the fact that what's happening in between them in terms of shock waves existing or not, this quantity remains a constant. This is basically, yes, it's basically the conservation of energy equation, but this quantity, A1 square over gamma minus 1 plus U1 square over 2 at state 1, so at station 1, must be equal to the same, and 1 is here, must be equal to the same thing at station 2 or state 2, let's say here. And this is also related in the equation that to a parameter called A0, and A0 is here. A0 is the speed of sound calculated using the stagnation temperature of the flow. So this quantity remains a constant. So it's my bad handwriting here, but it says constant. So so this quantity remains a constant, and we will start. We left off at this point in last week's class. So we start off from here. Now we will do a special case. That special case will be that we have the streamline and we have the fluid particles going from 1 to 2. We assume we will investigate, let's say, a special case where point 2 actually corresponds to a point such that at that point, velocity here will be equal to speed of sound, okay? And let's investigate that point. So if, so we go back to these equations and we say, so let's say a square over gamma minus 1 plus u square over 2 at a point on a streamline must be equal to now the same, as the equation written in a slightly different form. We use a different, now we introduce actually a different notation. We define a variable called a star. I will explain what this is in a second. A star square divided by gamma minus 1 plus a star square over 2 must be a constant for that special case. And that special case is at a point downstream in a flow, u is equal to a, so this condition. So, and also where at that condition where we have u is equal to u, the speed of the flow is actually the speed of sound, we will call this specific sonic velocity here a star. Okay, the value, because the temperature, a depends on temperature, right? So speed of sound depends on temperature, and temperature could be changing from 1 to 2. At a certain state where velocity becomes equal to a, whatever the temperature is at that current state will give me the value of the speed of sound at that point. I call it a star. The value of speed of sound could be different at 1, okay? But and if it for general condition, of course, it will have a different value at 2. But at the special condition that 2 is a condition where u is equal to a, at that condition I call it a star, or we define it in aerodynamics. It's not just I call it, right? It's in aerodynamics we define it as a star. So at the value of the speed of sound at that condition. So this a star here is this a star, and from this equation at the top, you can see I also replaced u with a star because u is equal to a star. So now I have this equation. Of course, under this condition, I can rearrange this equation a little bit. So I can write a square over gamma minus 1 plus u square over 2. Now I can take to a star parentheses, or actually a star square parentheses. This one becomes equal to gamma plus 1 divided by 2 times gamma minus 1 a star square. So this must be a constant. So the thing is, also maybe we can write the other equation that we had before. This is also equal to a0 square over gamma minus 1. Now we say, now let's talk about this for a second. We say this property is a constant, and when we say constant, what I actually mean is it is constant along a streamline. That's what I mean. So this property is constant along a streamline. Well, I mean, this term is a constant. We know that this is gamma for air flows, for example, gamma is equal to 1.4. So you just do the numerics. This is equal to a constant. So this is a constant. The right-hand side of this equation is a constant. So this says that for an adiabatic flow, for an adiabatic steady implicit flow along a streamline, a star is basically a constant. Okay, so 1, 2, streamline, a star does not change. And again, I will keep repeating this again and again, regardless of the fact that there is a shock wave or not. Okay, so a star in an isothermal flow, in adiabatic flow actually, is a constant along a streamline in an adiabatic implicit flow. A star is constant along a streamline in an adiabatic implicit flow. So we know that. And similarly, you can also see a0 is also a constant, right? Same equation from using the same arguments, you can also say a0 is also a constant. So these are important properties because we would like to relate, the shock downstream conditions to shock upstream conditions, but these results tell us that, yes, properties will change across a shock wave, air properties, air state, but some things will not change, some properties. So we will make use of this actually important physical concept. So returning back to this equation now, we will manipulate this a little bit. This equation here, we will play with it a little bit. So first, we will divide by a square over gamma minus 1, the entire equation. Let's say the whole equation. So when I do that, if I divide by a square over gamma minus 1, I end up with 1. So I'm dividing here this equation. So I end up with 1. So plus gamma minus 1 over 2 u square over a square must be equal to, for example, if I divide by a square over gamma minus 1 regarding the a0 square value, a0 square divided by a square, and similarly gamma plus 1 over 2 a star square divided by a square. This is what I get when I do this division. Of course, why did I do that? Because I would like to see Mach numbers in my equation. Until this point, I don't see any Mach numbers. And here it is. This is actually equal to Mach square in this equation. So just rewrite it again. 1 plus gamma minus 1 over 2 m square. Now, this is equal to a0 square over a square. So a0 square is equal to gamma times r times t0. And a is equal to gamma times r times t. And if we continue, this is equal to gamma plus 1 over 2. Similarly, I have a star square here. So I can write gamma r t star divided by gamma r t. Obviously, these terms, the constants actually cancel out, so these go away. So I end up with a relation between stagnation temperature and static temperature of the flow. So T0 over T is equal to 1 plus gamma minus 1 over 2 m square. So ratio of stagnation temperature, or sometimes we call it the total temperature, to static temperature, which means that at any point in the flow, at this point, if somebody gives you the Mach number, they say, okay, Mach number is equal to 2, and it's flying at 10 kilometers altitude, so temperature is probably around 216 Kelvin, okay? So at this point, this means that you can calculate the total temperature also, which means the total enthalpy of the flow at this point by just using this equation. If it's air, use gamma equal to 1.4, Mach number is 2, so it square is 4, and static temperature is 216 Kelvin. Let's say you multiply it, you will end up with the T0 value at this point. Why is this important? Well, first of all, the T0 value at this point calculated under these given conditions. Why is this important? Because of one very simple fact. This T0 value will remain constant along the streamline, okay? Again, I'm repeating, regardless of the fact that there is going to be a shock wave or not, okay? Not only that, this is only the first part of this equation. We have also this part. Not only that, we have also this part. So that part will give me a relation between the local static temperature and the T star value. T star over T will be equal to, again, a function of Mach number, 2 over gamma plus 1 multiplied by 1 plus gamma minus 1 over 2 m square. Okay, so this is the ratio, this is the T star over T, so T star is the temperature at sonic speed point, okay, ratio of temperature at sonic speed point, to local static temperature. Okay, this Mach number, again going back to the sketch here, this Mach number, of course, with this given temperature will correspond to some velocity, right? You can calculate, first of all, the speed of sound from temperature, and then use Mach number to calculate a velocity value. This velocity value obviously is not the sonic condition, because Mach number is not equal to 1 here. But if at some point on the streamline, for whatever reasons, the flow is, let's say, slowed down, decelerated, reduced speed down to Mach 1, so sonic condition is reached, the static temperature at this condition is called T star. And T star value can be calculated here. And similar to T0, this also remains constant along this streamline. So that is also the importance of T star. Whether there's a shock wave or not, T0 remains constant along the streamline. Going back to our arguments here, discussions here that we made, since A star does not change, T star also is a constant, regardless of the fact that there is going to be a shock wave or not in between 2 points in a streamline. So we have two very good, what I might say as a reference condition, which does not change with shock waves. Everything else will change. Mach numbers will change. Local static temperatures, local static pressures, densities, velocities, everything will change. But these two quantities will remain constant. T0, therefore A0, and T star, and therefore A star. This is very important in terms of shock and compressible flow aerodynamics, and in terms of obtaining shock relations that we will soon do. One thing that I can make one important note. Okay, before I do that, let me give you another interesting thing that is related to high-speed aerodynamics. Now it's related to this equation. Now T0 is important. Why? We said that it remains constant along a streamline, but it does have another very critical importance in terms of aircraft high-speed vehicle design. The importance is that we call this stagnation temperature, meaning that if you remember our first definition of stagnation properties, basically it represents the total amount of energy in the flow, meaning that if you somehow reduce the speed to zero velocity somewhere in the flow, adiabatically, without basically preventing any heat escape outside, so basically containing the all kinetic energy level, converting the entire kinetic energy level to internal energy level. That was a definition of stagnation conditions. Then you reach a certain temperature level, which will be quite high, because initially, let's say the fluid particle had an internal energy plus kinetic energy, but if you somehow force the kinetic energy to be zero, where will that energy go? It will turn into internal energy. The fluid particle will become very hot. The question is, does this happen in a flow field? Anywhere in a flight vehicle, high-speed flight vehicle, a fighter aircraft, or let's say a high-speed missile, does this happen on this vehicle? The answer to this question is yes, it does happen at the stagnation points, for example. At the stagnation points, which we defined in aerodynamics 1, if you remember, at the stagnation points, the velocity does become equal to zero. It becomes zero. So what will happen is at those stagnation points, the temperature of the gas which will be interacting with your flying object will be very, very high. It will be equal to your stagnation temperature. Well, you can ask, well, Professor, you're saying that it will be very high. Is it really high? I mean, is it really significant? I can give one example. So let's say this, just roughly, this is, let's say, 200 Kelvin. This is quite, let's say, I mean, above troposphere, this is 216 Kelvin, but I am just approximating it around 200 Kelvin. So let's say you're flying with Mach 2. What will be your T0? Let's calculate this. So T0 will be this 200 Kelvin times 1 plus gamma minus 1 over 2 is 1.4 minus 1 over 2. Mach is 2, so 2 square is 4, so this is equal to 0.2, so 0.8, so this is 1.8. This whole thing here is 1.8 times 200, so it will be equal to 360 Kelvin or so. Yeah, 360 Kelvin. It's not that high. I mean, it's okay, right? It's I mean, you cannot touch it with your bare fingers. It's about 80 to 90 degrees Celsius, quite hot. But I mean, for an aluminum vehicle, for a vehicle made out of aluminum or even composite material, it's not that bad. It's okay. So it's not that high. Well, the thing is, if you keep increasing the Mach number, this increases with the square of the Mach number. So let's consider another extreme case. So this is a typical case. Actually, Mach number is quite low. Maybe for a fighter aircraft, it's not that low, but for a missile, it's quite low. Let's say we have the same ambient temperature and we are talking about a hypersonic vehicle, let's say Mach 8, okay? Then T0 will be 200 times, so 1 plus, this is going to be 0.2 times 8 square, so 64, okay? How much is this? I have my calculator. Let me quickly calculate it for you. Siz benden muhtemelen daha hızlı hesaplarsınız ama. So this makes 13.8. So times 200. This makes 2,760 Kelvin. Okay, now this is high. This is not a happy situation. Okay, this is almost 3,000 Kelvin, and if you do not do anything as an engineer, your flying vehicle probably will melt away. Okay, and don't forget there's no heat transfer or anything here. It's just because of the fact that you are flying fast at high speed, hypersonic Mach number. So if you have a scramjet or whatever, this is your flight speed. So your vehicle will experience almost 3,000 Kelvin surface temperatures at the stagnation points. You have to have insulation, at least some kind of heat shield, and to prevent your vehicle from disintegration. And this problem even gets worse if you are, let's say, re-entering from space. So keeping the temperature constant, if your Mach number is, let's say, 20, okay? So this is going to be T0, 200 times 1 plus 0.2 times 20 squared. So 20 squared is what, 4,000? No, 400. Yeah, 400. And so this is, I guess, 81. 81 times 200, so it's almost 16,000 Kelvin temperature. Okay, guys, that's why you need a heat shield when you want to come back from space. Okay, your vehicle, space vehicle, capsule, or in the old times we had space shuttle, whatever, re-entering the atmosphere will face these temperatures. Okay, especially in the very first instance that the vehicle gets in touch with the atmosphere, it will be flying at extremely high Mach numbers. These are typical. And of course, because of as it enters more and more into the atmosphere, it will slow down to lower Mach numbers. But at the very first instance, the vehicle experiences extremely high temperatures, and it should survive this. So all these space vehicles are covered with very, very heat-resistant ceramic tiles, actually. Space shuttles and those capsules, and even if you're entering the Mars atmosphere, you know that there was a heat shield that protected the rover. I don't know if you followed it. So of course Mars atmosphere is a little bit different. Gamma is probably not 1.4, but anyway, so you could easily experience these temperatures. In 2003, if I remember correctly, there was a space shuttle accident. And what happened was during the launch of the space shuttle, an insulating foam on the fuel tank broke apart, and it flew away and hit the leading edge of the wing of the space shuttle. So space shuttle looked something like this. It had delta wings, and the foam that actually broke apart hit the leading edge of this space shuttle and actually damaged it. And actually, there was a hole. It damaged the heat insulation here. So it went up to space, it's fine. Astronauts worked there for a week or so, for 10 days. And then when coming back to Earth with the space shuttle, because of this hole at the leading edge and the damaged heat shield, of course, the temperatures are extremely high. These high temperature gases leaked into the wing and basically melted away the entire wing structure. And then it got, of course, totally destroyed. All astronauts were killed. So this is no joke. As aerodynamics engineers, if you're in the business of designing high-speed vehicles, we need to be aware of our aerothermodynamics. So after these, some important examples trying to pass you this information regarding the importance of stagnation temperature. Of course, we can use this relation to relate the property to stagnation pressure as well, because if you recall, what is this? The isentropic relations. If you remember, we have obtained these relations before in the semester. So basically, for example, the relation between stagnation pressure and stagnation pressure to static pressure ratio, it is related to T0 over T with an exponent gamma over gamma minus 1. But now we do have an expression for this one. So we can also write 1 plus gamma minus 1 over 2 m square to the power gamma over gamma minus 1. We also had an expression for stagnation density, rho 0, and I will directly write the equation from isentropic relations. This is also a function of Mach number as well. 1 plus gamma minus 1 over 2 m square, 1 over gamma minus 1. So this means that, again, if we are talking about a flow, a streamline in an adiabatic implicit flow, any point on the streamline, given basically the flight Mach number or the Mach number at this point, if this is given, that's actually all you need to do. That's actually all you need. I'm sorry, of course, gamma, I'm assuming gamma is given. That these are all you need, all parameters you need to calculate these ratios. P0 over P at that location, rho 0 over rho at that location, and obviously T0 over T at that location. And as I said again, if the flight altitude is given, which means you know T as well, from US standard atmosphere tables, you know T at that altitude, yeah, then you plug it in, you calculate, you can calculate also other variables. Yeah, so these relations P0, T0 over T, P0 over P, and rho 0 over rho being only functions of Mach number is quite useful in high-speed aerodynamics analysis and high-speed vehicle design. In fact, there's one more interesting thing. For example, we have the T0 over T relation, so divide T0 over T equation by T star over T equation. What we get is this: T0 over T is 1 plus gamma minus 1 over 2 m square. I'll write it down. And this is T star over T. This is equal to, so 1 plus gamma minus 1 over 2 m square divided by the other relation, 2 over gamma plus 1, 1 plus gamma minus 1 over 2 m square. If you do that, so basically this cancels with this. So this one becomes equal to gamma plus 1 over 2, which is equal to basically T0 over T star. That is interesting because if you remember, I said that along a streamline, adiabatic steady state inviscid flow, T0 is a constant, T star is a constant, and therefore A0 and A star are also constants. And that ratio, these are both constants, but these two constants are related with this equation. This is equal to gamma plus 1 over 2. So if for air, let's say gamma is equal to 1.4, so this is 2.4 divided by 2, so this is equal to actually 1.2 for air. So wherever you have, I mean, given flight Mach number conditions and altitude, you can directly calculate T0, and then you know that that number, numerical number, will be 20% about. I mean, T star will be about 20% less than the T0 value that you calculate. Yeah. So, so the temperature at sonic condition is known, T at sonic condition.
Hocam,
Is
the only way to change this ratio, should we change our working atmosphere?
If your working atmosphere is different, then yes, gamma will be different, and then this will be a different number. Yes, if you are in Mars, gamma will be different. This is not going to be equal to 1.2, but some other constant. I don't exactly know the gamma value for Mars atmosphere.
It's 1.16.
1.16. 16, 1.16 or 1.6?
Yes, 1.16.
16, so okay. It's mostly carbon dioxide atmosphere. So instead of 1.4, we have 1.16. You plug it in. This is your Martian atmosphere relation. If you want to fly at high speed at Martian atmosphere. Good.
In the T star over T equation, is it 2 over gamma plus 1 or minus?
T0 over T star.
So T star over T.
I'm sorry, I couldn't get your question. T0 over T star is gamma plus 1 over 2.
No, I asked T star over T equation.
T star over T equation. Okay. Did I write it wrong? Let me check. T star over T. It's up here somewhere. 2 over gamma plus 1.
Sorry, my mistake.
1 plus. It's correct, right?
Yeah, my mistake.
Tamam. Good. So yes, the temperature at sonic condition will be this number. It will be about 20% less than the T0 value. So not only that, I mean, not only we can estimate the T star value temperature at sonic condition, but similarly we can also obtain the, for example, the static pressure at sonic condition as well. We call it P star. And similarly, density at sonic condition, rho star, those can also be obtained. And those are also, let me write the equations. For example, P star, so this is the static pressure at sonic condition. Its ratio to P0 is actually also a constant. So this is 2 over gamma plus 1. I didn't derive it. I'm writing the equations directly. But yeah, you know, it's just from isentropic relation, basically. 2 over gamma plus 1, gamma over gamma minus 1. And similarly, we have the relation for density at sonic condition. We call it rho star. Over rho 0, for example, the ratio to the stagnation density, 2 over gamma plus 1 to the power 1 over gamma minus 1, again through isentropic relation. So, you know, see, we are basically getting lots and lots of information about the flow field. I mean, we are still, you know, these are just simple equations, right? Our starting point was basically the energy conservation equation. We started to play with the equations a little bit, defined the sonic condition, and we have now all these nice and very simple, actually, relations that define the physics of our flow field for a high-speed, high Mach number, or let's say at least supersonic, let's say, flow field. Now we will make another definition. This is quite important in high-speed aerodynamics as well. So first, remember our Mach number definition. We defined Mach number as you know, speed to speed of sound ratio. This is local flow velocity or magnitude of flow velocity, local speed, let me say. So let's say I'm referring to the magnitude of velocity here. And this is also the local speed of sound. So when I say local, I'm trying to say this. So again, we are considering a streamline. So if I select a point here, if I know the temperature here, this means that this will give me the local at this point, at this very point, the local value of the speed of sound. And if there is a certain velocity vector associated here, its magnitude is v. So that velocity vector's magnitude v divided by the speed of sound, this is how I define my Mach number. So this m is actually local value, right? Local value. Now we introduce a new definition in compressible aerodynamics calculations. This is also quite useful. We introduce what we call a characteristic Mach number. Let's say introduce characteristic Mach number, and we define it as m star. Okay, and this is defined as the local velocity v that we have in the Mach number relation here. This v is the same thing divided by a star. Okay, so this is again local flow speed, but now this is different. This is not local speed of sound anymore. This is speed of sound at sonic condition where we have temperature is equal to T star. Okay. This is m star is known as a characteristic Mach number, and it's very useful in supersonic flow analysis. Why? We will see probably today or tomorrow. But this definition is generally, it confuses you guys a lot, students a lot. So don't get confused. First of all, it is the ratio of the local speed to the speed of sound at sonic conditions. So it's not the ratio to the, it's not with respect to the local speed of sound. If somewhere on the streamline, I am reaching sonic condition, so T becomes equal to T star, this will correspond to an A star value. So basically this M star is the ratio of this velocity to this speed of sound, okay? The ratio of this velocity to this speed of sound is local Mach number anyway, okay? But M star is not that. Also, so basically for every local position, let's say at this point, I said temperature is T, local speed of sound is A, and I have a local Mach number because I have a local velocity. Similarly, I can also calculate a local M star value for every point of interest on this streamline. M star will have a value on this streamline. Why? Because A star, by the way, is a constant along this streamline. If you remember our discussions this hour, right? A star is actually a constant. Only thing that is changing in this equation will be your V. V will be changing if there is any pressure field or whatever, accelerating, decelerating, flow velocity can be different. So M star will have a different value at every point along this streamline. What will be the value of M star at sonic condition? That was a question, people.
Shouldn't it be 1?
It is going to be equal to 1 only here at the sonic condition. It is not going to be equal to 1, obviously, in other places, right? Do you understand this point? Because its definition compares the local speed to A star. It does not compare the speed at sonic condition to A star. I would like you to understand this very clearly, because generally students become very much confused about this definition of M star. But I think it's clear enough at this point. So once we introduce this characteristic Mach number definition, the next step is let's modify our original equations, which contained A star, and all that. Let's modify them a little bit, and let's start to see M star in those equations, okay? Why is this important? Again, it will be clear in a short while. So let's, if you do not understand this point, we are recording this class anyway, please rewatch this video, or please read some supplementary material from your book as well. So let's recall the energy equation we have. So I will rewrite it again here. So A square over gamma minus 1 plus U square over 2 was equal to gamma plus 1 over 2 times gamma minus 1 A star square. So we said this was a constant. We obtained this equation before. So now I want to see some Mach numbers in this equation. So let's divide this equation by U square. Okay. So if I do that, I get, for example, A square over U, or maybe it could be better if I just write A over U square divided by gamma minus 1 plus 1 over 2 basically, so U square disappeared. And on the right hand side, I have gamma plus 1 over 2 times gamma minus 1, and now a star over u square. Now you see where this is going, right? I get a Mach number from here, and I get the m star from here, basically. Okay, so just rearrange this, organize it a little bit, and actually I can solve for m square, local Mach number square. It's going to be equal to 2 divided by gamma plus 1 over m star square minus gamma minus 1. Okay, so now I have a relation between the local Mach number. Again, reminding you, by the way, here is I'm just thinking unidirectional flow, one-dimensional, so I'm only using one component of velocity u. So this is u over a, and I have m star, this is u over a star, basically. And remembering all the definitions that I just made a few minutes ago. So a relation between local Mach number and the characteristic Mach number, m star. Okay, we will continue from this point, or let me see. Okay, let me write this last equation, then let's give a break after that. Or if you solve for m, a local Mach number, you get this equation. You can do also, you can solve for m star value from this equation here, and get this expression. It looks like gamma plus 1 times m square 2 plus gamma minus 1 m square. So again, relation between m star and m, and it's important. Actually, this equation tells you more stories. It says the local m star value at any point actually is a function of Mach number as well. The local stagnation temperature is a function of Mach number, stagnation pressure, stagnation density, and on top of that, I'm sorry, m star value, the characteristic Mach number at every point, is also a function of local Mach number. And I'm not talking about gamma here. We are assuming we're operating in air, so we use gamma as 1.4. So it's basically a function of the local Mach number. It's 2:31. Let's give some break, and let's meet again at 2:40. Okay.
I sent you an email about the midterm one, but that was before I checked the dates on the website.
Yes,
So
I was going to tell you that the date is already on the calendar.
Yeah, I've checked it. Sorry.
No problem. Tamam, o zaman bir ara verelim, devam ederiz. Okay, everyone, so let's continue. So we defined, we now have a relation between the characteristic Mach number and the local Mach number. We will see, I hope I can reach that point today, maybe tomorrow we will reach that point, that this characteristic Mach number is the main parameter that we will use to relate the shock, the downstream of shock conditions to the upstream of shock wave conditions. We will actually derive an equation related to that. So it's therefore very important. But anyway, this equation here that we derived, m star is actually a function of Mach number, or the vice versa, the left equation here. If you investigate it, for example, for certain cases, if Mach number is equal to 1, local Mach number is equal to 1, which means we are actually at sonic condition. Okay, we are actually at sonic condition. Of course, at that location, m star is also 1. Okay, so we know that. If Mach number is less than 1, so we are basically talking about a subsonic flight condition, then m star, if you calculate it from this equation, you will see that m star is also less than 1. if m is greater than 1, so supersonic flight condition, you will see that m star value at that location is also greater than 1. So m star basically behaves physically and mathematically very much similar to Mach number, except for only one important difference. For the special case of m local Mach number going to infinity, well, mathematically that is, or more practically you can say going to very large numbers, okay, high Mach numbers, then m star does not go to infinity. From these relations, actually m star converges to a finite value, and that value is equal to square root of gamma plus 1 over gamma minus 1. So as, let's say, m goes to infinity, Mach star converges to this value. Okay, so this property is actually very nice and actually quite important, and we will make use of this when we are deriving normal shock wave relations. Okay, this mathematical property of m star. So anyway, so now after, I mean, at this until this point, we've actually built up quite a bit of background regarding energy conservation, regarding definition of speed of sound, regarding how we utilize this definition of speed of sound in energy conservation equation, regarding how we actually define this characteristic Mach number and how are these quantities are all related, stagnation quantities, star quantities. So now we will make use of this background knowledge for our ultimate purpose, which is the calculation of normal shock properties. We will actually go back to our very starting point, calculation of normal shock wave relations. Normal shock wave relations. Okay, we at the very beginning, if you remember, when we first started talking about shock waves, we actually started doing this already. Except at that stage, we did not have all this detailed information yet. Now we learned it, and we will apply all this information regarding star quantities, stagnation quantities, and all that. And what we did back then was we said, okay, there's a shock wave, and we will take a control volume across the shock wave. That's what we did, how we did it before. And we use this control volume. We said here is, let's say 1, here is 2. And we, using this control volume, we derived some basic governing relations in which we did not have any Mach numbers, nothing. So I will rewrite those conservation equations. From the conservation equation, conservation of mass equation, we got this relation, for example, ρ1 u1 is equal to ρ2 u2. From the conservation of momentum equation, we got this. P1 plus ρ1 u1 square is equal to P2 plus ρ2 u2 square. And from the conservation of energy, we know that H1 plus u1 square over 2 is equal to H2 plus u2 square over 2. So we got these before when we did the control volume analysis. And here there are some equation numbers. Let me write these down. So let's say this is equation 1, 2, and 3. And of course, we can relate, we have two more relations in reality. We can relate H H to temperature. So for example, H1 is equal to Cp times T1, and H2 is equal to Cp times T2. So this is, let's say, equation 4. And we have the equation of states, which relates separately. P1 is equal to ρ1 RT1, and similarly P2 is equal to ρ2 RT2. Let's call this equation 5. So that basically constituted a complete equation set for us to calculate temperatures, pressures, or not calculate, but I can say relate temperatures, pressures, and everything. So now, starting from this point, we will do some manipulations to these equations and combine them, or not combine, but I can say introduce the new things that we learned now regarding this adiabatic inviscid flows, for example, energy conservation. So starting from here, our first step is divide the momentum equation by the continuity equation. So divide equation 2 here, which is the momentum conservation equation, this one, by equation 1, which is the mass conservation equation, which is here. So if I do that, I get this relation, P1 over rho 1 U1 plus U1 is equal to P2 over rho 2 U2 plus U2. Okay, and I can rearrange this to look like this: P1 over rho 1 U1 minus P2 over rho 2 U2 is equal to U2 minus U1. So this looks a little bit more interesting. The velocity difference and the pressure difference are now related. And in my notes, we call this I call this equation 6. Now we start to introduce the definition of speed of sound. So remember, we know that a square is equal to gamma RT, or we can also write this is equal to gamma times P over rho from if we make use of equation of state. So let's say use this in equation 6, which is just here. So this looks like now, so I have P over rho here, as you can see, right? This is P over rho, and I do have P over rho here in the A square. So this is basically A square over gamma. So this becomes equal to A1 square over gamma U1 minus A2 square over gamma U2 equal to U2 minus U1, equation 7, I called it. And now this is a combination of continuity and momentum. So don't forget that this is continuity plus momentum. This is representing that. Energy is not here yet. Now we make use of this energy equation in alternate form. So energy equation in alternate form, as we have discussed mostly today. And this equation looked something like this: a square over gamma minus 1 plus u square over 2 is equal to gamma plus 1 over 2 times gamma minus 1 a star squared. So this was the energy equation in alternate form. Now I would like to make use of this as well. In addition to what we got in equation 7 here, I would like to make use of this equation. So first of all, for flow region 1, so before the shock wave, and when I say 1, if you can refer to my control volume up there, I don't want to scroll the whiteboard again. So flow region 1 is before the shock wave. So flow region 1, I can write from this equation, basically from the energy equation alternate form, that A1 square before the shock wave actually can be written as gamma plus 1 over 2 A star square minus gamma minus 1 over 2 U1 square. So this is before the shock wave. And maybe I should write here before the normal shock wave, that is. And after the shock wave, so for region 2, I can write a similar expression now for A2, the speed of sound after the shock wave, can be written as gamma plus 1 over 2 A star square minus gamma minus 1 over 2 U2 square. By the way, call it equation 8, call it equation 9. I don't know if you can see where this is going. We will write these equations in a second, but you can see speed of sound before the shock wave, velocity before the shock wave, and A star, which does not change across the shock wave, as we have been discussing. A2, speed of sound after the shock wave, U2 after the shock wave, A star value remaining constant through the shock wave. So you may get a feeling where this is going now. It will be related to Mach numbers, M1 and M2. And of course, keeping A star basically a constant will help me do that, help me get a relation between them. So now we get these two equations, 8 and 9. Now I have basically I have an expression for A1 and A2 and when I make use of the energy equation. Where do I need A1 and A2? Well, I need them here in equation 7, which is the combination of continuity and momentum only. Now, if I insert that A1 and A2 here, it will be a combination of continuity, momentum, and energy conservation. One equation representing basically all the physics. If I do that, so let's write that. So substituting 8 and 9 to 7, yes. And of course, after you need to do a little bit rearranging and everything, we get this relation. Gamma plus 1 over 2 times gamma times U1 times U2 multiplied by U2 minus U1 times A star square plus gamma minus 1 over 2 times gamma multiplied by U2 minus U1 must be equal to U2 minus U1. Okay, so now this basically, just a little note here, is physically representing, this equation is physically representing continuity plus momentum plus energy conservation for the flow through a shock wave. Okay. Manipulate one more step, meaning divide by U2 minus U1, because I see it everywhere in the equation. Divide by U2 minus U1. And what I get is gamma plus 1 divided by 2 gamma U1 U2 times A star square plus gamma minus 1 over 2 gamma is equal to 1. Okay, so it looks a little bit more simplified. And if I would like to solve for A star from here, if you solve for A star square will be equal to simply U1 times U2. Okay. So how did I get from here to here? Solve for A star square. So you just need to rearrange the equations. Well, in compressible aerodynamics, this relation is known as Prandtl relation. Okay, and it is basically the backbone of normal shock wave relations, relating state 1 before the shock wave to state 2 after the shock wave. It is the backbone of this analysis, equation 10 here. Why? Because of this. Because if you recall, if you remember the characteristic Mach number definition, M star, this is equal to U over A star, right? This is how we defined it. Local velocity divided by the speed of sound value at sonic condition, and make use of this relation now, and in Prandtl relation. How? For example, I can rewrite let's say rewrite Prandtl's relation using this definition as this. I can say I can basically divide both sides by a star. So divide both sides by a star square, actually. Both sides by a star square. What do I get? I will get 1. So I'm dividing this one, both sides by a star square. So 1 will be equal to u1 over a star times u2 over a star. So of course, obviously, this tells me an important story. It says, well, m1 star times, which is this, times m2 star must be equal to 1. Okay. So why is this so nice? Because it says that, well, look, if I can scroll up, my whiteboard is getting frozen. We are talking about the shock wave. We have before the shock wave, after the shock wave conditions, and some probably incoming supersonic flow towards this shock wave. We are talking about an adiabatic inviscid process. So which means that in a one-dimensional flow, let's say there will be a streamline going like that from 1 to 2, right? And if we know, for example, somewhere in 1, in the first state, the m star value and 1 star value, okay, which can be calculated, right? Because m1 star means that you need to know u1 and you need to know a star value. And we have just, and u1 is basically related to local Mach number, if this is given, and local T1, so you can calculate u1. A star is basically, can be calculated through T star, and T star is a function of Mach number. So everything can be calculated, and 1 star can be calculated. Well, guess what? As soon as you have a number for M1, you do know the number for M2 star because of this relation here. Because M2 star will be simply 1 over M1 star. That's it. So we have a very solid and very, very simple relation, equation that relates the upstream of the shock wave gas properties to the downstream of the shock wave gas properties. Okay, and not only that, so let's call this equation 11, by the way. Not only that, so this is the backbone. Let's say this is the backbone. I name it like that. This is the backbone of normal shock wave relations. Normal shock relations. Everything starts from this relation. How? Because, for example, this says M1, M2 star, M1 star, but what is M star? We already have an equation for this, right? Just at the end of the previous hour, we said we know that M star is a function of local Mach number. And let me write that relation again here. Gamma plus 1 times m square. So in this case, if you're interested in 1, so you just write 1 here. And then 2 plus gamma minus 1 m1 square. And well, and of course, so this is that. And we also can write separately an equation for m2 star, which is also now written in terms of the local Mach number after the shock wave. So M2, 2 plus gamma minus 1 times M2 square. Well, these two are related. And one, I mean, related meaning, by the way, this is also square, right? Related meaning, you know, if you multiply these two, because M1 star times M2 star must be equal to 1. So if you multiply this, I mean, the square root of this with the square root of this, that must be equal to 1. Well, that directly now gives me a relation between M1 and M2. Okay, so the Mach number, supersonic Mach number incoming towards a shock wave, and the Mach number after the shock wave. So if you basically use these two relations here, use these two, plug them into into this relation, we get the following equation. So we get so substituting into equation 11, we get this relation. So gamma plus 1 and 2 square divided by 2 plus gamma minus 1 and 2 square must be equal to gamma plus 1 and 1 square divided by 2 plus gamma minus 1 and 1 square to the power minus 1. Well, now if you solve this equation for M2, because I want to know the Mach number after the shock wave, here is what we get. M2 square is equal to 1 plus gamma minus 1 over 2 and 1 square divided by gamma times m1 square minus gamma minus 1 over 2. So now this is nice, because if someone is interested in calculating the Mach number after a shock wave, after a normal shock wave, and given an upstream flight condition, only thing that you need to know is Mach 1, your supersonic flight condition, if you're flying at Mach 1.2, 1.5, Mach 2, Mach 4, Mach 8, this equation directly gives you what will be the Mach number right after the shock wave, theoretically, okay? Right after the shock wave. So this is quite nice, because again, I'm assuming we are moving, I mean, gamma is known, basically, for any gas. Air is 1.4, carbon, Martian atmosphere is 1.16, but that is known. So only thing I need to know is my upstream, or basically, if it's a high-speed flight vehicle, my flight Mach number. If you know M1, and if there's some normal shock wave that is created in the flow in front of this incoming M1, and there you have it, you can directly calculate your M2. So this is our first relation relating, first relation that helps me to calculate the, one of the parameters after the shock wave, which is probably the most important parameter, the Mach number after the shock wave, only using a single parameter, which is M1. So, of course, I said M2 is the most important parameter, but it's not obviously the only parameter. We need to determine all other variables as well. I mean, I need to know, for example, temperature after the shock wave. I need to know the static pressure after the shock wave, the density after the shock wave, even the entropy after the shock wave. So now, starting from this point, once I have this relation, I can do all the rest. Okay. So basically, our what we are interested in is that we have a normal shock wave here, and then 1 and 2 here. Now I have a list of variables. Given inlet conditions, that is, M1 is given, so I can calculate M2. But U1, P1, ρ1, temperature, stagnation enthalpy, even entropy and stagnation pressure, I want to be able to calculate same variable set after the shock wave. And our only equation is just relating Mach numbers at this stage. Okay, so the thing is, let me see. The thing is, how are we going to do that? I mean, how are we going to actually calculate the rest of the parameters? The thing is, let's say if you first concentrate separately on region 1 and region 2. So we have, let's say, a straight streamline going through the shock wave. So let's say we concentrate on the region, we have 2 points here before the shock wave and 2 points here after the shock wave. Now the question is, can we use, for example, isentropic relations that we have derived before to calculate all the variables after the shock wave? The thing is, what I'm trying to say is, for example, can I relate, I mean, isentropically, I know that, for example, I can relate stagnation pressure at 1 to static pressure at 1 through Mach 1. So I know that this is 1 plus gamma minus 1 over 2 and 1 squared to the power gamma over gamma minus 1. I can do that because of the fact that everything before the shock wave is basically can be considered to be isentropic. I can do also similar thing for after the shock conditions, meaning I can relate 1 plus gamma minus 1 over 2 and 2 square gamma minus 1 over 2. I can do that for these 2 points. These 2 points in among themselves are here isentropic. But what I cannot do is I cannot use these or similar relations like T0, T, rho 0, rho. I can, which we call isentropic relations, right? I cannot use those relations across the shock wave because shock wave is not itself, it's not an isentropic process. Or it is, or let me put it this way, it is not a reversible process. It's what we call an irreversible process. It is adiabatic, but it is not reversible. Okay, so it is maybe I could put a note here: irreversible process, though adiabatic. It is adiabatic, but not reversible, and our condition, so therefore not isentropic. Okay, the shock wave itself, as we have discussed in the very beginning, is a very thin layer in the flow field, in the airflow, with a very high viscous, which generates very high viscous losses. So there's lots of friction involved, lots of viscous effects involved. So it's not a reversible process because of this physical fact. It is adiabatic though. There is no external Q dot or anything that is incoming. This is zero. But so therefore, the fact that it is an irreversible process makes it a not isentropic process, a non-isentropic process. So therefore, entropy also must be changing across the shock wave, which means that we cannot use isentropic relations like this when we want to relate 1 and 2 together. Okay. So this is important, which in terms of equations, what I'm trying to say is, for example, I cannot relate, for example, the static pressure after the shock wave to the static pressure before the shock wave through an isentropic relation. For example, I cannot do this. For example, P2 over P1 is equal to, let's say, rho 2 over rho 1 to the power gamma, for example. I cannot do this. Okay, this is not allowed. If you write this in the exam, you will get 0. This is not allowed. This is because of the fact that we cannot use isentropic relation across the shock wave. if I would like to repeat myself. Then what are we going to do? I mean, using isentropic relations was one of the options, and now it's out of the question. I mean, I can do this and I can do this, but I cannot do this. So this is out of the question. Then what are we going to do? Because I still need all this list of parameters, right? So we go back to our conservation equations. The first one, for example, from conservation of mass, we write rho 1 u1 is equal to rho 2 u2. I can make this equation look like this: rho 2 over rho 1. So that's the density ratio now across the shock wave, which I am interested in. I would like to know that. It says it's equal to u1 over u2. Okay. And I can also write this as u1 square over u1 times u2. Okay. And from our just equations that we have seen about maybe 15-20 minutes ago, I can write this one as u1 square over a star square. This is Prandtl's relation. Instead of u1 times u2, I wrote a star square. Well, look what we got here. This is equal to m1 star square. Okay. So if you are interested in finding the density ratio across the shock wave now, it's simply equal to m1 star square. Okay. And what is m1 star square? We have already written this equation now a few times already. So m1 star square is equal to, it's a function of m1 square, gamma plus 1, m1 square, 2 plus gamma minus 1, m1 square. So it's that's it. If you're interested in finding the density ratio across the shock wave, just this gives you that. Only thing that you need to know is your flight Mach number, which is supersonic. Otherwise, you wouldn't have a shock wave. So your supersonic Mach number, you plug it in this equation, it gives you also the density ratio. That is quite nice. So therefore, in addition to the Mach number M2, now I also know rho 2 after the shock wave. Across a normal shock, therefore our normal shock wave relation rho in terms of density ratio is this. I will rewrite it again formally so that you know that this is actually the normal shock wave relation for density ratio across a shock wave. So this is now across a shock wave, a normal shock, that is. Yeah. Good. So I solved two of my problems. I know how to calculate M2 at this stage after the shock wave. I know how to calculate rho 2 after the shock wave, of course, given rho 1, of course. I'm assuming the before the shock wave conditions are given. So I know how to do that. What about the others? Pressure, for example. So for that, now we make use of the momentum equation. I think these 2 hours we have talked about lots of stuff. You might be feeling a bombardment of information, but it's nice that we are recording these sessions. So I strongly suggest you watch this again if you don't feel comfortable or if you did not understand some points. From the momentum equation, it gives us actually P2 minus P1, which is equal to rho 1 u1 square minus rho 2 u2 square. By the way, what we learned so far is really not that difficult. It's just simple equations, right? We don't even have any differential equations, anything. It's just simple algebraic equations. Important thing is to match these very simple equations with the physics that you need to learn, the concept. So please, go over these video again, class video. I suggest that. But we know that from continuity, rho 2 u2 is equal to rho 1 u1. So from here, the momentum equation looks like this: P2 minus P1 is equal to now rho 1 u1 square minus, instead of rho 2 u2, I will write rho 1 u1 again, rho 1 u1 times u2. So this becomes equal to rho 1 u1 square 1 minus u2 over u1. Good. Now I divide this by P1. So I want to see on the left-hand side this ratio, P2 minus P1 divided by P1, which is basically P2 over P1 minus 1. I want to see this ratio relating static pressures now, before and after the shock wave. That becomes equal to rho 1 u1 square divided by P1 times 1 minus u2 over u1. Okay, good. Now I see here a gamma, I'm sorry, a P over rho here. Okay, rho 1 over P1. Instead of that, I can actually write a gamma over A1 square. So now speed of sound comes into play. So this becomes equal to gamma times U1 square over A1 square. So now I have the Mach number. That is nice. 1 minus U2 over U1, which I will directly write. So this will become equal to now gamma times M1 square 1 minus U2 over U1. Okay. So that is nice. I see Mach number and on the right-hand side, and on the left-hand side, I see static pressure ratio across the shock wave. I'm interested in that. I just don't know what this is, U2 over U1. Actually, I do know that because from continuity, I know that rho 2 over rho 1 is equal to U1 over U2. So I can forget about this. Instead of U2 over U1, I can write rho 1 over rho 2 here in this term. Instead of this term, I can write that. So if I do that, and by the way, I mean, why is it important that I can write that? Well, I know this one. I know this is a functional Mach number, which I already got before a few minutes ago. So from here, if I combine all of this, P2 over P1 minus 1, or I can take it to the right-hand side. So it becomes equal to 1 plus now gamma times M1 square multiplied by 1 minus 2 plus gamma minus 1 and 1 square divided by gamma plus 1 and 1 square. So written in a little bit more neater form, now I get a static pressure jump relation across the shock wave, which looks like this. 1 plus 2 times gamma divided by gamma plus 1 times M1 square minus 1. Now I have a relation for static pressure change across a shock wave, across a normal shock wave. So what do we have now? I know how to calculate M2 after the shock wave. I know how to calculate rho 2 after the shock wave, and I do know after the shock. I do know how to calculate the P2 after the shock wave. So my list is growing bigger. Okay. So this is the third normal shock wave relation regarding static pressure change across the shock wave. And again, the nice thing is only a function of inlet Mach number. Similar to the case that we had for the density. It was also only a function of the inlet Mach number. And also for M2, which was also only a function of inlet Mach number. My list is not ended yet because I need to know temperature. Well, that is going to be quite straightforward. T2, that is the temperature change. I want to know what is T2 after the shock wave. And for that, I use equation of state. from equation of state. I mean, why do I want to use equation of state? Because it relates pressure to density to temperature. I have already obtained expressions for pressure and density. So that's nice. I can just take temperature out of this picture. So I can get T2 over T1, temperature rise across, I mean, I'm saying rise because I do know temperature increases across the shock wave. So P2 over rho 2 divided by P1 over rho 1 from equations of state for each state. So this is equal to P2 over P1 basically times rho 1 over rho 2. Well, this is nice because I know I just obtained an equation for this. That's fine. And I obtained an equation for this somewhere up above in my page. So I just need to multiply these two functions together in order to get the temperature ratio across the shock wave, which looks like this. Is equal to 1 plus 2 gamma. I will write it gamma it's plus 1 and 1 square minus 1. So this was the pressure ratio basically times the density ratio reversed. So 2 plus gamma minus 1 and 1 square divided by gamma plus 1 and 1 square, everyone. So this is the temperature ratio across the shock wave. And by the way, if you just multiply temperatures by Cp, it's also equal to the static enthalpy ratio, right? Because Cp times T2, Cp times T1. So this one is now the temperature ratio. Oops. Anyway, you see what I'm saying. T ratio now across a normal shock wave. So now I know how to calculate M2, P2, rho 2, and T2. That is nice. I got most of what I wanted. I have few more things left. I got most what I wanted. I know how to calculate temperature, pressure, density, and Mach number after a normal shock wave. Well, as you have seen here, I mean, we will continue tomorrow, but what I would like to say is this. These equations are simple equations. I mean, you can just, type this equation, Excel, and calculate this temperature ratio, right? You don't have to solve a differential equation, no numerical method or anything. It's just algebraic equation. You plug it in, boom, you get the results. Plug it into the pressure ratio, you get the pressure after the shock wave. So it's quite nice algebraic equations. And even it's, in order to make your lives even easier, or our lives as aerospace engineers even easier, the results of these relations are already calculated and tabulated at the end of books. For example, if you look at the end of your aerodynamics book, you will see tables which shows you listed under the name of normal shock wave relations, and for air, for example, given gamma, for different M1 inputs, it's already calculated from the table. You can directly see your temperature ratio, pressure ratio, density ratio, and there are several others. But you can do it yourselves also, MATLAB, Excel, Python, whatever, just plug in these equations. This means that now you are capable of handling supersonic flying vehicles, okay, with these simple theoretical equations. Of course, you will do some experiments with shock waves this semester, and you will do some visualization regarding oblique shock waves, which are based on these equations as well. We will see later. And you will compare your observations with theory that we are learning. So this is how we handle high-speed flying vehicles, people. This is whether you're designing them for Martian atmosphere or Earth atmosphere or Jupiter's, Moon's atmosphere, Titan atmosphere or whatever, Saturn's moons. This is how you handle high-speed flying vehicles. If high-speed meaning supersonic flying vehicles, that is. This is how you handle the conditions. You have a way to calculate these properties, and because we are interested in knowing pressures, temperatures, and densities, because our vehicle basically is traveling behind the shock wave as it's flying supersonically, right? It is basically sitting inside this shock wave, so it's getting exposed to the conditions after the shock wave. So we need to know these conditions to understand the temperature on our vehicle, the pressure on our wings, you know, the lift, therefore the lift characteristics, the loading on our aircraft, all are determined due to these conditions after the shock wave, because as I said again, as I'm saying again, our vehicle is sitting behind the shock wave with respect to the flow. Good, so our list is mostly complete here, list meaning here, but we need few more characteristics. For example, what will be S2? Entropy. Is it going to be, we know that it's not equal to S1 because it's a non-isentropic process, but how do I calculate S2? Is it also a function of only input Mach number? And after that, we will also calculate, for example, I mean, given these, you can calculate, for example, T02, which we already know that this is equal to T01. But what is P02, for example? How do we calculate that? So after those, our list will be complete. And so, by the way, let me write this down here as well. Our list will be complete, and once we are given all inflow conditions, a Mach inflow state of the gas at 1, we know how to calculate the state of the gas at 2 if there's a normal shock wave sitting somewhere there. Okay, so let's stop here. And we will continue from entropy calculation in tomorrow's class. Okay, any questions? Okay, great. So let me stop recording, and